There is a filing cabinet at the SETI Institute in Mountain View, California, that contains something extraordinary. Not extraordinary in the way that word gets used in press releases. Not extraordinary meaning impressive or noteworthy. Extraordinary in the original sense. Outside the ordinary. Beyond what the ordinary framework of science can comfortably accommodate. That filing cabinet contains decades of anomalous radio detections, signals that arrived at our telescopes with characteristics that did not match any known natural source, that were logged, flagged, examined, and then filed away without a satisfying explanation. Not filed away because they were dismissed, filed away because nobody could figure out what to do with them. I want to be precise about what I mean when I say nobody could figure out what to do with them, because that phrase can mean very different things in science. Sometimes it means the data was ambiguous, the signal too faint or too brief to characterize properly, the noise too high to draw any conclusion. That is ordinary scientific uncertainty, and it is handled routinely. What I am describing is something different, something that happens less often, and that the scientific community is, I think, genuinely poorly equipped to process. I am describing signals that were clear enough to characterize, that had specific measurable properties, that could be studied and analyzed, and that after all the studying and analyzing did not fit any natural explanation that anyone has been able to construct. That is a different kind of not knowing. That is the kind that makes careful scientists quiet. I have spent my career working at the boundary between what physics understands and what it does not. I have watched how the community responds to anomalies, how the response changes depending on what domain the anomaly comes from, and how differently we treat anomalies in radio astronomy compared to, say, anomalies in particle physics or cosmology. And one of the things I have noticed, one of the things that I think deserves to be said out loud more often than it is that the radio astronomy community has an anomaly problem that it has never fully confronted. A collection of signals that have been arriving at our telescopes for 40 years, that have resisted every natural explanation that has been seriously proposed, and that sit in that filing cabinet because acknowledging them publicly carries a cost that most researchers are not willing to pay. I want to take you through these signals today, not in the way they are usually discussed, not with the breathless excitement of a documentary that treats every unexplained phenomenon as evidence of alien contact. I want to take you through them the way a physicist looks at anomalous data, carefully, honestly, with full attention to what the alternative explanations are, why some of them work and why some of them do not, and what is left over after all the natural explanations have been applied as generously as possible, because what is left over, I think, is genuinely interesting, not in the tabloid sense, in the scientific sense, in the sense that means we have data that our current models do not fully explain, and that is always, in my experience, the most important place to pay attention. Let me start at the beginning. The 15th of August, 1977. Astronomer Jerry Ehman is sitting at a desk at Ohio State University going through computer printouts from the Big Ear radio telescope. Big Ear was a remarkable instrument, a fixed radio telescope built into a field in Delaware, Ohio, that scanned the sky as the Earth rotated, listening for radio signals at the frequency of 1,420 megahertz. That frequency is not arbitrary. It is the frequency at which neutral hydrogen, the most abundant element in the universe, emits radio waves. It was proposed by physicists Philip Morrison and Giuseppe Cocconi in 1959 as the most logical frequency for any technologically advanced civilization to use if it wanted to send a detectable signal, because any civilization that had developed radio astronomy would know that other civilizations were listening at that frequency. Ehman is going through the printouts looking for anything unusual. The data comes in columns of numbers representing signal intensity, and most of it is exactly what you expect from a radio telescope pointed at blank sky. Low numbers, noise, background, and then he sees it. A column of numbers so far above the background noise that he circles it in red pen and writes a single word in the margin. Wow. The signal lasted 72 seconds, exactly the length of time Big Ear could observe any fixed point in the sky as Earth rotated. It was centered precisely on 1,420 megahertz. Its intensity reached 30 times above the background noise level, which in radio astronomy terms is an enormous signal-to-noise ratio. It had a shape, a rise and fall, that exactly matched what you would expect from a point source moving through the telescope's beam as Earth rotated. Everything about it, the frequency, the duration, the intensity, the shape, matched perfectly what you would expect from a narrowband radio signal originating from a fixed point in space at an enormous distance. Eamon's exclamation has been known as the wow signal ever since. And 47 years later, despite everything we have learned about the universe and despite every instrument we have pointed at that region of sky, we have never detected it again. We do not know what it was. We do not know where exactly it came from. We do not have a confirmed natural explanation for it. Now, I want to do something that is important here, something that discussions of the wow signal often skip. I want to take the natural explanations seriously because they deserve to be taken seriously, and because understanding why they fall short is what makes the remaining mystery meaningful rather than just mysterious. The most straightforward natural explanation is terrestrial interference. Radio frequency interference from human technology, aircraft, satellites, military transmissions is one of the primary challenges of radio astronomy. It mimics astronomical signals, it comes and goes unpredictably, and it has fooled careful researchers more times than anyone in the field likes to admit. Could the wow signal have been a human-made transmission that happened to pass through the telescope's field of view at the right moment? The answer is probably not, and here is why. The signal was centered on 1,420 megahertz with extraordinary precision. Transmitting at that frequency is internationally regulated and largely prohibited because it is a protected band reserved for radio astronomy. The probability that a rogue transmission would hit that exact frequency at that exact intensity with that exact beam shape is very small. Not zero, but very small. And the shape of the signal, the smooth rise and fall that matched a point source tracking through the beam, is hard to replicate with a local source moving at the speeds typical of aircraft or satellites. A more sophisticated natural explanation involves interstellar scintillation. Just as starlight twinkles when it passes through Earth's atmosphere, radio signals can be amplified and distorted when they pass through clouds of ionized gas in interstellar space. Could a normally faint natural source have been momentarily amplified by a chance alignment of interstellar gas into a brief, intense signal? This is a legitimate possibility. Scintillation is real, and it does produce temporary amplification of radio sources. But the amplification factors required to produce a signal 30 times above background from a previously undetected source are very large, and the frequency stability of the wow signal, its precise centering on 1,420 megahertz, is difficult to explain through scintillation, which tends to affect a broad band of frequencies rather than a single narrow channel. The explanation that has received the most serious recent attention came in 2017, when astronomer Antonio Paris proposed that the wow signal was produced by a comet. Two comets, 266P, Christensen and P, 2008. Y2 were passing through the relevant region of sky in August 1977, and Paris argued that clouds of hydrogen gas surrounding comets, called comae, could produce radio emissions at 1,420 megahertz. This got a lot of press coverage. It was presented in many outlets as the wow signal solved. but the explanation has serious problems that the press coverage largely ignored. Subsequent observations of these comets with sensitive radio telescopes did not detect the predicted 1,420 megahertz emissions at anything close to the required intensity. The hypothesis required the comet's hydrogen coma to be extremely dense and positioned just right, and when researchers actually pointed telescopes at comets to test this, the predicted signals were not there. The 2017 announcement turned out to be premature, and most radio astronomers who have looked carefully at the cometary hypothesis remain unconvinced. Where does that leave us? It leaves us, honestly, without a satisfying natural explanation for a signal that arrived at our telescopes with exactly the characteristics we would expect from an intentional narrowband transmission from a distant source. I am not saying it was aliens. I want to be completely clear about that. I am saying that the best natural explanations we have proposed do not fully account for the data, and that after 47 years of trying, we are still in that position. But the WOW signal, remarkable as it is not the anomaly I most want to talk to you about today. It is the most famous anomalous radio detection, but it is not the most systematically interesting one. The signals I find more compelling, more scientifically challenging, and more resistant to dismissal are a class of phenomena that were only discovered in 2007 and that have been arriving at our telescopes, we now know, for billions of years. They are called fast radio bursts. A fast radio burst is exactly what the name suggests. A brief, intense pulse of radio energy lasting anywhere from a fraction of a millisecond to a few milliseconds. Extraordinarily bright, extraordinarily brief, and arriving from cosmological distances, from galaxies billions of light years away. When the first one was discovered in 2007 by astronomer Duncan Lorimer and his student David Narkovich, while they were going through archival data from the Parkes radio telescope in Australia, the initial reaction of the community was the same reaction that greets most anomalies in science: skepticism. Surely it was interference. Surely it was some instrumental artifact, something local and mundane that happened to look like a signal from deep space. But then more of them arrived from different telescopes in different parts of the world, pointed at different parts of the sky. By now we have detected well over 1,000 fast radio bursts. They come from all directions. They show the characteristic signature of having traveled through intergalactic space, a dispersion of frequencies that tells us they pass through billions of light years of ionized gas on their way to us. They are unambiguously real. They are unambiguously extragalactic. And while we now have some partial explanations for some of them, the full picture remains one of the most actively debated problems in astrophysics. Let me tell you what we know about fast radio bursts, because the details matter and they are more interesting than the usual summary suggests. The energy involved is staggering. A typical fast radio burst releases in a few milliseconds more energy in radio waves than the sun releases in thousands of years. The power output for those brief moments rivals or exceeds the total energy output of entire galaxies. Whatever is producing these events is operating at a scale of violence that has very few parallels in the known universe. They disperse in a way that tells us exactly how far they have traveled. Radio waves at different frequencies travel through ionized plasma at slightly different speeds, with lower frequencies arriving slightly later than higher frequencies. This dispersion measure, as it is called, is a direct probe of the electron density of the intergalactic medium along the line of sight, and it allows us to infer the distance the burst has traveled. The dispersion measures of fast radio bursts tell us they come from distances ranging from hundreds of millions to billions of light years. These are not local events. They are coming from across the observable universe. Most fast radio bursts appear once and never repeat. You detect a burst, you look at that location again, and there is nothing. No afterglow, no persistent source, nothing to indicate what caused the event. This is one of the features that makes them particularly hard to study, because by the time you can point additional telescopes at the location, the event is over. But some of them repeat. A small fraction of fast radio burst sources have been detected multiple times, sometimes many times, sometimes in complex patterns. The first repeating source, discovered in 2016 and designated FRB 121102, has been detected hundreds of times. Some of these repeating bursts arrive in clusters, with many bursts occurring over a period of hours or days, followed by silence for weeks or months. The repeating sources have allowed us to localize them precisely enough to identify their host galaxies. FRB 121102 comes from a small dwarf galaxy about 3 billion light years away. The source sits within a region of that galaxy with a very high star formation rate, surrounded by an unusually dense and magnetized environment. Another well-studied repeating source, FRB 20201124a, comes from a galaxy about 1.5 billion light years away and shows bursts that arrive with changing polarization properties that suggest the source is embedded in a complex, dynamically changing magnetic environment. Now let me tell you about the leading explanation for fast radio bursts, because it is important to understand what the mainstream scientific view is before I tell you why some researchers find it incomplete. The leading explanation is magnetars. Magnetars are a type of neutron star, the dense remnant left after a massive star explodes in a supernova. Neutron stars are already extreme objects, packing more than the mass of our sun into a sphere roughly 20 kilometers across. But magnetars have something additional. They have magnetic fields of extraordinary strength, 1 trillion times stronger than Earth's magnetic field, strong enough that the quantum mechanical properties of space itself are altered in their vicinity, strong enough that the energy stored in the magnetic field exceeds the gravitational binding energy of the star, strong enough that when the magnetic field suddenly restructures itself in an event called a starquake or a magnetic reconnection event, the energy release can be comparable to a fast radio burst. In 2020, a significant piece of evidence arrived in favor of the magnetar hypothesis. A magnetar in our own galaxy, SGR 1935 plus 2154, produced a radio burst that, while much fainter than extragalactic fast radio bursts, had the same basic characteristics. It was brief, it was bright, it showed the same dispersion signature. For the first time, we had an observation linking fast radio bursts to a known astrophysical object. The magnetar hypothesis moved from plausible to strongly supported. But here is where the story gets complicated. And this is the part that does not make it into most of the popular accounts. The magnetar hypothesis explains some fast radio bursts reasonably well. The non-repeating ones, the single events from distant galaxies, could plausibly be magnetar starquakes. Violent one-time events that release enormous energy and then subside. But the repeating sources are harder. A magnetar can, in principle, produce multiple bursts, and magnetar starquakes can recur. But the specific patterns of some repeating fast radio burst sources, the way the bursts cluster in time, the way the polarization properties change from burst to burst, the complex substructure within individual bursts, these are difficult to explain with the magnetar model as currently formulated. There is a repeating source, FRB 201211102a, that has shown bursts with substructure at the microsecond timescale. Microseconds. The timescale of the substructure within a single burst implies a source region smaller than a few hundred meters. Think about that. Something the size of a small city producing in microseconds more radio energy than our sun produces in years. The magnetar model requires the emission to come from specific regions of the magnetosphere, and matching the observed substructure requires fine-tuning of the model that makes some researchers uncomfortable. There are also statistical patterns in some repeating sources that have attracted attention. Several groups have reported evidence for periodicity in the arrival times of bursts from certain sources, periods ranging from hours to days. If the bursts from a given source arrive preferentially at certain phases of a regular cycle, that suggests the source has a clock of some kind, a rotation period, an orbital period, a precession period. Magnetars do rotate, and the rotation periods can explain some of these cycles. But the range of periods observed and the precision with which some of them repeat has pushed theorists to consider more complex models involving binary systems, orbital dynamics, and geometries that are increasingly elaborate. And then there is the sub-second periodicity. In 2022, a team of researchers reported the detection of a fast radio burst source FRB 20191221A that produced a burst lasting nearly 3 seconds, far longer than typical, with a clear periodic substructure. The bursts within the event repeated every 0.2 seconds with remarkable regularity. The team argued that this periodicity was consistent with a rotating neutron star, a pulsar-like object, but one producing radio bursts at a rate and intensity that no known pulsar has ever matched. The source was in a galaxy about 1 billion light years away, and if it was a neutron star, it was a neutron star behaving in a way we had never seen before. The 0-2 second period is significant for a reason that I want to dwell on, because it is one of those details that gets mentioned in passing in technical papers, but that deserves more attention. The rotation rates of neutron stars span an enormous range, from millisecond pulsars that rotate hundreds of times per second to slow pulsars that rotate once every few seconds. A period of 0.2 seconds is within the normal range for neutron star rotation, so the magnetar explanation cannot be ruled out on those grounds alone. But the energy output of this source, the rate at which it was emitting radio bursts, and the extreme regularity of the substructure are all pushing at the edges of what the magnetar model comfortably accommodates. Now I want to take you somewhere that the published papers rarely go, because I think it is where the most honest scientific thinking about fast radio bursts leads, and because it connects to the broader question I want to leave you with at the end of this conversation. One of the features of fast radio bursts that has been most discussed in private conversations, in the hallways at conferences, in the back channels of the field, is their narrowband nature. Radio emission from natural astrophysical sources tends to be broadband. Stars emit across the whole electromagnetic spectrum. Synchrotron radiation from electrons spiraling in magnetic fields covers a wide range of frequencies. Thermal emission from hot plasma is broadband. But fast radio bursts, while not as narrowband as the WOW signal, tend to occupy specific frequency ranges, and the emission within a burst often shows frequency drifting patterns where successive subbursts arrive at progressively lower frequencies in a pattern called the sad trombone effect. That pattern was completely unexpected from natural emission mechanisms, and while there are now theoretical models that can produce something like it in a magnetar magnetosphere, those models require specific conditions that are not always present. The sad trombone pattern, and I'm going to be honest about what I think when I look at it carefully, looks more like what you would expect from a signal that has been frequency modulated, a signal whose frequency has been deliberately varied over time, then it looks like what you would expect from a natural emission process. I am not saying it is frequency modulation of an artificial signal. I am saying that when you look at the pattern without the prior assumption that it must be natural, it has a character that invites that comparison. And the fact that the comparison invites itself is worth noting. Let me now tell you about a class of signals that is less well known than the WOW signal or fast radio bursts, but that I think deserves more attention than it gets. These are the anomalous signals that have been detected not by SETI experiments specifically, but by large-scale radio surveys conducted for other purposes. Surveys mapping the distribution of hydrogen in the galaxy, surveys looking for pulsars, surveys characterizing the radio sky for cosmological studies. In the data from these surveys, researchers have occasionally flagged signals that did not fit their expected source models. Signals that were coherent, narrowband, appeared briefly at specific positions on the sky, and then did not repeat. Most of these signals have been attributed to interference, and many of them probably are. But the rate at which anomalous signals appear in these surveys, cleaned of obvious interference and analyzed carefully, is higher than the expected rate of random false positives. It is not dramatically higher. It is not high enough to make headlines, but it is persistently, quietly, stubbornly higher, and it has been higher across multiple surveys conducted over decades. This is the kind of statistical anomaly that is very easy to dismiss and very hard to explain. It could be a systematic error in how the interference models are calibrated. It could be a population of unusual natural sources that we have not yet characterized. Or it could be something else. And the fact that we cannot distinguish between these possibilities is not a failure of the researchers who have flagged the anomaly. It is a failure of our current theoretical framework to make predictions specific enough to test. I want to be direct about something here because I think it is important and because I think the scientific community has sometimes been less than fully direct about it. The question of whether any of these signals, the wow signal, fast radio bursts, the anomalous detections in survey data, could be of artificial origin is a scientifically legitimate question. It is not a question that belongs only to science fiction. It is a question that follows directly from the logic of physics, from the Drake equation, from our understanding of the age of the galaxy and the number of potentially habitable planets it contains. If technological civilizations can arise, and we are existence proof that they can, and if they can develop radio technology, which is a fairly early stage of technological development, and if any of them are old enough and motivated enough to be transmitting signals into space, then those signals would look like radio signals. They would travel at the speed of light. They would show dispersion consistent with interstellar travel. They might be narrowband, because narrowband signals are more easily distinguished from broadband noise, and they would arrive at our telescopes mixed in with all the natural radio emission from the universe. We would not necessarily be able to tell them apart. That is the honest answer. With current technology, with current signal processing, with current theoretical models that were built around the assumption of natural sources, we might not be able to distinguish an artificial signal from an unusual natural one. Not reliably, not in every case. And this means that the filing cabinet at the SETI Institute contains something more ambiguous than I think is usually acknowledged. It contains not just signals we cannot explain naturally, but signals we cannot rule out as artificial. That is a different and in some ways more unsettling category. It means the boundary between explained and unexplained is not where we have drawn it. There is a broader point here that I find myself returning to when I think about this field. We have been searching for signals from technological civilizations for about 65 years, since Frank Drake pointed the first dedicated radio telescope at two nearby stars in 1960. In that time, we have developed increasingly sensitive instruments, increasingly sophisticated signal processing, increasingly wide coverage of the sky and the frequency spectrum, and we have not found a confirmed signal, not a single one that has passed every test and been verified by independent observations. Most scientists take this as evidence that technological civilizations capable of transmitting detectable radio signals are either rare or absent in our galactic neighborhood. That is a reasonable interpretation. It might be the correct one, but there is another interpretation that I think deserves more consideration than it usually receives. We have not been searching for very long. 65 years is a cosmic eye blink. We have not searched the whole sky comprehensively. We have not covered the full frequency range. We have not accounted for all the possible ways a signal might be modulated or encoded. We have not considered seriously the possibility that signals might not look like what we expect signals to look like, that a sufficiently advanced civilization might transmit in ways that our current instruments would not recognize as a signal at all. And we have, I think, been too quick to file away the signals that do not fit our models. The WOW signal has been waiting for an explanation for 47 years. The anomalous survey detections have been accumulating for decades. Fast radio bursts are real, are extraordinary, and while we have a leading natural explanation for some of them, that explanation does not comfortably accommodate all of them. There is a principle in physics that I find myself invoking more and more in this context. It is not a formal law. It is more of a heuristic, a rule of thumb built from the history of discovery. The principle is this: when a phenomenon keeps resisting explanation, when the explanations keep requiring more and more special conditions and more fine-tuning, the resistance is often a signal that the explanatory framework is wrong, not that the phenomenon is just unusually complicated. We applied this principle when the anomalous perihelion precession of Mercury resisted Newtonian explanations for 40 years. The explanations kept requiring additional planets, additional masses, additional special conditions. The resistance was telling us that the framework was wrong. The framework was Newtonian gravity, and the correction was general relativity. We applied this principle when the anomalous spectral lines of stars resisted classical explanations for decades. The resistance was telling us that the framework was wrong. The framework was classical atomic physics, and the correction was quantum mechanics. I am not saying that the anomalous radio signals are telling us we need a new physical theory. I am saying that 40 years of signals that resist natural explanation might be telling us something, that the explanation might require not a more complicated version of the models we have, but a different kind of explanation entirely. An explanation that involves, at least in some cases, the possibility that we are not the only species in this galaxy that has learned to broadcast into space. I want to be careful about what I am and am not claiming, because this is a topic where imprecision causes damage. I am not claiming that the WOW signal was sent by aliens. I am not claiming that fast radio bursts are alien transmissions. I am not claiming that the anomalous survey detections are messages waiting to be decoded. I am claiming that we have, across 4 decades of radio observation, accumulated a body of anomalous signals that resist natural explanation, that sit in filing cabinets and databases because acknowledging them publicly carries a cost that most researchers prefer to avoid, and that the resistance of these signals to explanation deserves more serious attention than the field has been willing to give it. Not breathless excitement, not sensationalism, serious scientific attention. The same serious scientific attention we give to anomalies in particle physics or cosmology, without the additional burden of potential ridicule that attaches to anything that sounds like it might be about aliens. Because here is the thing about that burden of ridicule. It has distorted the science. It has caused researchers to be more aggressive in dismissing anomalous signals than the data warrants. It has caused papers proposing natural explanations to be published before those explanations have been fully tested. It has caused a field that should be one of the most open to extraordinary findings to be one of the most defensive about them. And the irony is that the question we are really asking, are we alone in this galaxy, is one of the most important questions in the history of human inquiry. It is a question with implications that extend into every aspect of how we understand our place in the universe. If the answer is yes, we are alone, then our existence is a cosmic accident of a profundity that is almost incomprehensible. If the answer is no, then the universe is inhabited, and the silence we have been hearing is something we need to understand. Either answer matters. Either answer changes things. And the signals in that filing cabinet, 40 years of unexplained radio detections, narrowband pulses from the hydrogen line frequency, extraordinary bursts of energy from galaxies billions of light years away, brief detections that appear and vanish without repetition, they might not be telling us the answer, but they are telling us something. They are telling us that the universe is producing radio phenomena at a rate and with a character that our current models do not fully account for. And in my experience, that is the most important thing a data set can tell you. Look up at the night sky. Right now, radio waves are passing through your body, thousands of them. Radio waves from pulsars, from supernova remnants, from the cosmic microwave background, from galaxies billions of light years away. Some of those waves have been traveling for longer than the Earth has existed. Some of them originated in events so violent that the physics of the source is still not fully understood. And somewhere in that torrent of arriving energy, somewhere in the electromagnetic rain that falls on us constantly from every direction, there may be signals that we have detected and filed away because we do not know what to make of them. That is where we are. It is an uncomfortable place, but it is an honest one. And I would rather stand in honest uncertainty than retreat into the false comfort of a filed away anomaly that we have pretended is resolved because the alternative is too interesting to think about carefully. The signals have been arriving for 40 years. We do not know what they are, and that, for now, is the most truthful thing I can say. If this sits with you, if you find yourself thinking about what is in that filing cabinet and what it might mean, I want to know. Tell me in the comments which of these signals you find most compelling and why. Tell me what you think the honest scientific response to 40 years of unresolved anomalies should be. I read these conversations, they matter to me. And subscribe if you want to keep going deeper into the places where the known and the unknown meet, because that boundary is where the most interesting things always happen.